All right, y'all. Welcome back to DB Chemistry. We're still on the kinetic molecular theory. We're now on structure 1.1.2. And today we're going to be talking specifically about kinetic molecular theory as how we explain physical properties of matter, the states that they're in, solids, liquids, and gases, and those changes of states. We're going to be able to distinguish between the different states of matter in a variety of different ways. And we're going to be using state symbols, solid, liquid, gas, and aqueous in chemical equations. Now, we're not going to be doing any big chemical equations. We're just going to be doing state changes. But nevertheless, we will be using solid, liquid, and gas. We will cover the names of different states and those state changes: melting, freezing, vaporizing, evaporating, and boiling, condensating, sublimating, and deposition. Or depositing. So with that, we're just going to jump right in. So we've already described that we have three states of matter. Well, three states of matter that matter. We have our solids, which we use the state symbol S. We have our liquids, which we use the state symbol L. That's a cursive L. We use cursive because non-cursive just looks like a one. And we have gas. Now, gases, we use the state symbol G. There was one more state symbol that we had brought up, which was AQ. That means aqueous. And that's when we dissolve something in water. So if we have salt water, NaCl in H2O, we would say that's NaCl aqueous. And that would say that we've dissolved it in water. We also have other ways to represent, but we'll get to that further down in our DP chemistry curriculum. Now, there's also one more state of matter that's plasma. Plasma is just generally referred to as ionized gas. Ionized gas. Again, that's a concept we'll cover later, but it's not very important for our DP curriculum. And this is found mostly in outer space, mostly in outer space. So today we're just mainly going to focus on solids, liquids, and gases. And we're going to be using those state symbols: S for solid, O for liquid, G for gas. All right. Now, before we talk about those three states of matter, to just understand these states of matter, we're going to be using what we call kinetic molecular theory. Kinetic molecular theory is often abbreviated KMT. And along with it, when we use kinetic molecular theory, we start with a couple assumptions. Basically, this tells us to assume a few things about all matter. So the first one that we assume is that matter is made of small particles. These small particles can be very much like what we talked about before with particles when we're talking about substances. So these could be atoms, these could be compounds, but all matter is made up of small particles, and that's our first assumption. Uh, in addition, these particles all have kinetic energy, which I'll abbreviate to KE. Now, kinetic energy is the energy of motion. So, kinetic generally refers to motion. So, this is the energy of motion. And because they all have kinetic energy, this comes with another assumption. So, they all have kinetic energy, which causes these particles to be in constant motion. So in KMT, our particles are always moving. Solid, liquid, gas, doesn't matter. These particles are always moving. Furthermore, another assumption is that the amount of kinetic energy, again, I'll abbreviate to KE, is proportional to temperature. So what that means is that we have more motion at higher temperatures. You can kind of imagine that if you're walking slowly throughout a room, you feel kind of cool. But if you start running and you just start running around like crazy, you're going to start warming up. You're going to start heating up. And you can kind of think of particles the same way. The faster they're moving, the hotter they are. All right, the last and final assumption that we make with kinetic molecular theory is that any collisions between particles are elastic. Elastic is a word that we use in physics to describe collisions that there is no energy loss. So what we mean by elastic is that we have no KE loss. So that means when you have two things like maybe two billiard balls that collide, we know that's not an elastic collision because we hear sound. That's energy that's being lost to propagating sound waves through the air. But if two atoms collide elastically, there is no energy loss. There is a full transfer of energy from one to the other and vice versa. We have no energy loss. So kinetic molecular theory kind of assumes a perfect world for energy transfer. So what we're going to be doing is that we're going to be using KMT to describe our states of matter. In addition to the states of matter, we're going to be describing those state changes as well. So let's go back to our three states of matter that we're going to be focusing on: solids, liquid, and gas. Again, we're not focusing on plasma. We're not focusing on an even rarer one, which is bosons and condensate, which is less energy than a solid. We're just talking about solids, liquids, and gases. So if we look at the particles in a solid, you can generally think of them as being very close packed. So if we have some container and they're just sitting in this container, they're going to be very close packed. They'll probably be sitting at the bottom. We would say they have a fixed position and they vibrate. Remember, they're constantly moving. Just because a solid has low energy doesn't mean the particles aren't moving. They're moving just less than a liquid or gas. Now, in a liquid, we have particles kind of all willy-nilly. No real fixed position. They're on top of each other. You'll notice they still sit at the bottom of the container. We say these particles are held together, but they can still move around. They're kind of sliding around each other. They're always in contact with another particle, but they move left and right, up and down, as long as they stay next to each other. Lastly, we have a gas. Now, these particles are spread out and they're constantly moving. I'm going to try and illustrate a concept here. So they're spread apart and they move in straight lines. They still follow Newton's laws where once in motion, they'll continue in motion, and they're not going to be moving or diverging from their pathway. They'll move in straight lines. They're in constant motion. You'll notice they're not held together in any way, shape, or form. If we look at the kinetic energy trend, we have an increase in kinetic energy. So, this is how they look on the particle level. We're going to talk a little bit about what defines them. So we have our solids first. In our solids, we cannot compress them. There is no compression. The solids are already very closely packed together, as we can see here. They can't really get any closer to each other. Furthermore, they have very strong attractive forces holding them together. Strong attractive forces. Now, I do want to make something clear. When I say the word strong and strong attractive forces, I don't necessarily mean that they're going to be stronger than forces in a liquid all the time. But what I do mean is that they are strong enough relative to their environment to hold these particles in this fixed position. So, one of the ways that we describe solids is that we say they have a fixed volume and shape. If you look at our little cube, or not necessarily cube, but rectangle of atoms, they're not going to change into this liquid where they fill the bottom of the container. They're just going to kind of stay where they are and they're going to hold this position. Furthermore, their volume will stay constant as well. Now, if we move over to our liquids, much like solids, there is no compression. So liquids will not compress. If you fill a water bottle with water all the way to the top, not a single air bubble, and you squeeze it, you won't be able to squeeze that water bottle because there's nowhere for that water to go. So we say there's no compression. They do have some attractive forces, but we say weaker attractive forces. And the specific thing about this weaker attractive forces is they allow for particles to flow. They allow for particles to flow, which brings up another property that we'll get to much later on called viscosity. But because of those attractive forces, particles can flow past one another. When we talk about a liquid, we often say there is a fixed volume because, once again, we cannot compress it, but no fixed shape. If you go ahead and take your water bottle and you empty it into a glass, you'll notice the water enters the glass in very much the same way it did before. So if I have, let's say, an Erlenmeyer flask, a long test tube, or a beaker, and I have the same volume of water, it doesn't really matter what the shape of the container is. It will always fill the same amount. So whether we pour it from one to the other, it really doesn't matter the shape of the container, but it may always remain like, let's say we had 5 milliliters, it would always be 5 milliliters on each of these. And it wouldn't change one way or another because the volume is the same. All right, lastly, we have gas. Now, gas is very compressible. So we say it can be compressed. If you take that same water bottle and empty it out and screw the cap on, you will find that you can still squeeze it. Or you take a balloon and you fill it with some air, you can still squeeze that balloon into a smaller area. Furthermore, if you take maybe a basketball, I'm going to do my best to draw a basketball, and you take the same one, you'll notice you can pump them to different amounts. You might have it at 30 psi, which is the pressure, and you might have it at 40 psi, which means that there's more air here, but it's the same volume. Because you can compress the air, you can add more in, the particles just get closer together. Furthermore, we say they have the weakest attractive forces. When we move into this idea called ideal gases, at the end of structure one, we actually assume that they have no attractive forces. For all intents and purposes, we generally assume that these particles don't attract each other. They don't influence each other at all. And because of this, we refer to gases as having no fixed shape or volume. They can flow, so we'll add that here, can flow, and they can compress, and they can fill whatever container they're in to the shape of that container. All right. So now we have all these ideas for kinetic molecular theory. Let's go into the properties. So the first property we're going to talk about is density. Density is an important one because it tells us specifically the mass per volume of any substance. And so we generally measure it with the equation density equals m over v. There's one density you should always know. Pure water has a density of 1.00 grams per milliliter, or also another way to say it is grams centimeter minus 3. You'll notice the IB quite often likes to use this sort of notation where they put all of the units on the same line, and a negative 3 just refers to the same thing as grams per centimeter cube. That centimeter unit is on the bottom. That's what this little negative indicates. Anyways, um, density is mass per volume. Generally speaking, solids have a high density all the way to gases, which have a low density. And somewhere in the middle, we have our liquids, where they don't have a high or low density, more medium. But something to note is that liquids are actually much closer to solids than gases. Liquids generally have, oh, wrong marker. Liquids, liquid density is much closer to solid than gas. What I mean to say is gases usually have about 1,000 times, even more than that, less density than liquids or solids. All right. Now, the last part of this section is we're going to be talking about changes of state. All right. So what does it mean to change state? Well, before we even say what it means, well, you generally know going from solid to liquid, liquid to gas, or whatever. We also call this a phase change. Phase change. This is referred to as a physical change. Something about that means it's also reversible. You generally know this because you can take ice, melt it to a liquid, and then turn it back into a solid by sticking it in your freezer. And something else about this is that the physical change will occur. So the state will change as kinetic energy increases, increases, or decreases in a substance. Now, at the top, we mentioned that we're going to be using equations to represent changes of state. So why don't we look at an example of ice melting? So generally, ice in its solid form is referred to as H2O, and we'll use the state symbol solid. Then, as we apply heat, and remember, if we look further up, we can see that, oh, where did I put it? Right here, the amount of kinetic energy is proportional to the temperature, so more motion at higher temperature. So as we apply heat, we're going to have more motion, we're going to have more kinetic energy, and the ice, my mistake, will turn into H2O liquid, and that's ice melting. We can further boil water by taking this H2O liquid and apply more heat, and we'll get H2O gas. And so here we have a phase change from solid to liquid and liquid to gas. And these changes are reversible. You'll notice that when it's hot outside and you have a cold glass of ice water, the gaseous water in the air will condense into liquid water droplets on the outside of your cup. Furthermore, if you take the water in your cup and you stick it in the freezer, you will get some ice cubes that you can pop out of your ice cube tray. So these changes are completely reversible, and that's by removing heat. So the exact opposite. The last thing we're going to discuss is these state changes. So if we look at our solid, oh, I want to go back to my white. If we look at our solid and we look at our liquid and our gas, we have these phase changes. And so we generally know some of these already. When we take our solid and we turn it into a liquid, we call that melting. When we take our liquid and turn it back into solid, we call that freezing. When we take our liquid and we turn it into a gas, we call that vaporizing. Now, you may know a different word for that. You may think of it as boiling, but boiling is only half of it. We'll cover that in a moment. When you take your gas and you turn it into a liquid, we call that condensing. Melting, freezing, vaporizing, condensing. And then lastly, when we take our solid and turn it into a gas, these are the ones that usually stump students a little bit. So solid to gas is called sublimation or subliming. Generally, you see this with dry ice. So if you ever seen dry ice, that's frozen CO2, that's solid carbon dioxide, and it will immediately turn into a gas. Furthermore, gas back into a solid, we call that deposition or depositing. And again, that's actually the reverse of dry ice. If you freeze dry ice, if you put, for example, you blow up a balloon with your own breath, which has carbon dioxide in it, maybe a really big balloon, and you put it in a really, really, really cold freezer, you'll get a tiny little bit of dry ice. Um, so those are our changes of state. I did mention before this closes out, I'm going to go over vaporizing. Vaporization. It actually breaks into two subcategories. We have boiling, and we also have further down evaporating. I'm going to clarify a couple things. Boiling happens at the boiling point. So that is the temperature at which the substance goes from liquid to gas. You've seen this with water, so maybe 100 degrees Celsius for H2O. You generally know that off the top of your head. And this happens throughout the liquid, happens throughout the liquid. If you boil water in a pan, so if you have a pan or a pot over a fire, oh, I want to grab my highlighter out for that one. You've probably boiled water for pasta or something like that. You'll generally notice these bubbles form at the bottom and rise up. Now, the only reason they form at the bottom is that's where it's the hottest. It's generally like 100 degrees Celsius here, but at the top it might be like 99.8 degrees Celsius, only because it's interacting with the cooler air. And so the boiling is going to happen at the bottom. But if you were able to get that temperature uniform throughout your liquid, the boiling would happen everywhere. Now, evaporating is a little different. Evaporation happens at any temperature, but it only happens at the surface. And you may notice this as well. For example, if you step out of a pool, and I'm going to draw a hand. Now, I'm not known for my art skills, and that's all right. And you've got droplets of water on you. Let's just say you have a bunch of droplets of water on you. Only at the surface of these droplets will these water molecules leave. And eventually, these droplets will grow smaller in size. Trying to show us. They will eventually become smaller in size. Whoop. And these molecules will continue to go until there is no water left on you. This only happens at the surface, and I'll show you why in detail. Now, this is the end of the video, so if you want to end it here, feel free. If you want to stick around to really see evaporation, well, stick around. Here is a cup of water, and we're going to represent the molecules of that water with little dots. So, like I said, you do not need to stick around for this to see evaporating. But basically, what happens is these particles are all moving around. They're just kind of shaking around, moving, flowing around each other like crazy, and they're bumping into each other. And when they bump, they give each other their energy, kind of like when you have a cue ball, or kind of like when you're playing pool and one ball hits another ball. That's going to make that new ball move and that old ball stay. Now, the same thing happens here. These particles might run into each other, and I'm going to zoom in and maybe get a clearer color. And they might transfer their energy all into one particle, which that particle is going to then have enough energy to break its bonds and leave. And that process right there is evaporation. Now, you might ask yourself, well, why doesn't it happen inside? Well, it could if one particle ends up getting all that energy. So let's say this particle right here ends up getting a lot of energy, and boom, it wants to leave. Well, it's just going to run into another particle and then transfer all that energy to it, which that will transfer all that energy to it, which that will transfer all that energy to it, until it transfers its energy to another particle which is not locked in, and that particle will also leave. So that can only happen at the surface where it doesn't have any more particles to run into. And so that's how evaporation works. If you stuck around this long for the incredibly long explanation, congrats. Otherwise, have a great day. I will post all these notes in the description of the video, and hopefully this helps you with structure 1.1.2.